Hello, welcome back to Stochastic Processes class, and then today we'll be checking continuous time Markov chain. So let's check the first definitions. We have a stochastic process x of t, given that t belongs to a time variable of 0, infinity, closed interval 0 and open interval infinity is called is called a continuous Markov chain if it has the following three properties. The first property is that the state space of our stochastic process is finite or countably infinite, very important. Then property 2, the index set of our stochastic process is continuous, that is our x subscript t, where t equals to 0, 1, 2, 3, 4, etc. They are continuous, which have to do with their time. So our time is continuous. So, and also our stochastic process has the Markovian properties, that is the probability of our next state, which consider the x and then t, the current state time and the next state time is t. It's given that our current state at time x is equals to I, our previous state is given as u. Then the result is that our next state, our future state, is only dependent on our current state at time s equals to I, and our next state, which depend on the current on the time of yesterday, or our current state, then our future time, then is equals to j. So our I, j, k are all possible state space of that particular stochastic process, and our time x and time t are greater than or equals to 0. Alright, so another definitions for this is that consider a continuous time stochastic process s of t where our t is greater than or equals to 0. It's a discrete state space, that is a finite or a countable infinite state space. We say that the stochastic process is a continuous time Markov chain, or we call it Markov jump process if it satisfies the following property. And the first thing, that for any sequence of a real number satisfying 0 less than or equals to t0 less than t1 less than t index n less than t index n plus 1, we have our stochastic process whereby we have our next state to be I index n plus 1 if our first state for that stochastic process is t0 equals to I0. Our next state of that stochastic process is still at t1 equals to I1 to our very current state, which is tn, and we have this state space to be I subscript n is equals to only that our future state depends entirely and alone on our current state, which is t index n equals to I subscript n. So in order for us to understand this concept better, so we can take this example that let our stochastic process s of t denotes the weather condition. From 5 a.m. and then to 11 a.m. and the state space and x, which is the state space, equals to rainy, this is sunny, windy, rainy and cloudy, raining and then cloudy. Now let's just assume this to be the possible weather condition we can have. Then we have our time t to be closed interval 5,11. So graphically, we can illustrate this. Okay. So let's have our here be our time in hours, and then here be our state space of our S of t. So we have sunny, windy, raining, and then cloudy. So let's say these are possible states we can have. Wherever we have 1, 2, 3, 4. So let's say this is raining, this is sunny. Sorry, let's start from the first element in our state space. We have sunny, windy, raining, cloudy, and then our times, which is continuous, from 5, 6, 7, 8, 9, 10, and 11. So let's say at time 5, the weather condition is just, let's assume that's in between windy and rainy. So we have something like this here. Then for the next state X, so let's say our state at time 6, we have the weather condition is between sunny and windy. Then by the time we are moving to time 7 a.m., at 7 a.m. we are having kind of changing, maybe like raining to cloudy. At 8 a.m. I assume that we have it is raining. It is definitely raining. And at 9, let's say that it is now there's now a wind. Or yes, maybe there's now between sunny and wind. And then at time 10, we now have maybe it's kind of cloudy, which is still possible. Then at cloudy, so we have something like raining. The cloud has gathered, maybe like raining. So here now we know that it's the gradual state, that it moves gradually from 5 a.m. to 6 a.m. There are a lot of time. What happened at 1 minute after 5? What happened at each seconds? Okay, I think our time. Okay, our 5. This is 5 hours. Okay, that's a.m. rather. So at 5 a.m. okay, what happened? That is between 5 and 6 we have countable infinite time, that is 5 a.m., 5:01, 5:02, 5:03, 5:04, 5 until 6 a.m. So we can easily check what happened between those hours of time. So, and also from 6 we move to 7. From 7, there's a gradual movement. We also move to raining at time 8, and then from time 8 we move to 9, and from 9 we move to 10, then we move back to 11. So with this help of stochastics, with this help of continuous time Markov chain, we're able to know what actually happened in between these hours of time. I hope that is taken. So in this continuous Markov chain, we make an assumption. We make some certain assumption. Says that we assume that the probability of our next state will depend on the current time of our current state, plus the time it will take for our next state is equals to j, given that our current state at time x is equals to I, is independent of our time x, which is greater than or equals to 0. So at this point, say the process T, where the process, the stochastic process, and this particular assumption of h of t, stochastic process of h of t, is said to be time homogeneous. It's time to be homogeneous, or have the homogeneous property, or have the homogeneous property. That is, the probability of our next state is our x plus t minus our current state is equals to x of t, x of t. That is, if you want to just check for x plus t, and then we are independent of x, we just have our x of t, and our t is the changes in t, whereby is equals to 0, infinity. So what we are talking about is that if we have our non-IDs, whereby we have our time 0, we have our time at x, we also have our time at t. Okay, here we have our I, and then here we have our j. So from here to here is our x minus 0, which is equals to x. But for this t, you can say that our t here is equals to t plus x. From here to here is x, from here to here is t. So from here down here now, it will be t log x, which is what we have here. Okay, sorry, this is I, and let's assume this to be I. Okay, let me call it k. So our current state here is I. So for our next state t, it will be the addition of this. But if our x of t here, if our current stochastic process at this time t is independent of this our x, that is this our t plus x, is if from here to here is x, and then from here to here is t plus x, then we can actually get from here to here. So from here to here will be what we have at j, which is t plus x, then minus what we have at I, which is x, and that is why we have x of t. I believe that is clear enough. So at this point we say that we have a time homogeneous, that is, our time is independent of the current time state, in order to predict the next state, which only depend on time t. So here we will stop for the definitions of our continuous time Markov chain. In our next video, we'll be checking the transition probability. Thank you for watching. See you in the next video.